Hi, it's Mr. Anderson. Welcome to Biology Essentials Video 46. This is on communities. This podcast and the next podcast both deal with ecology. Ecology is a fairly recent science. If we break down the word, eco comes from the Greek word oikos, which means house. And so it's the study of our house. So it's the study of life on our planet and how they interact. And when you're studying ecology, there are a few terms that you want to kind of understand. And so the way I remember those is Babekpo. So I stutter on the B. So Babekpo is going to tell you all the different levels we study within ecology. So if we start at the beginning, that'd be biosphere. But I like to start down here at the bottom. And so on Babekpo, if we start at O, or the organism level, we just finished, remember, talking about organ systems. And so cells make tissues, tissues make organs make organ systems, and organ systems makes organisms. And so an organism would be one individual, like this bull elk here in Montana. If we have a group of elk living together, that's now a population, or all the elk in Yellowstone Park would be a population. If we have not only the elk, but the wolves and the willow and the aspen and all of that together, now we're at the level of a community or populations interacting. If we add the abiotic factors or the non-living factors, now we're at the level of an ecosystem. So this would be a picture of the greater Yellowstone ecosystem. It's not going to only include the elk and the wolves and the bison, but it's going to include the temperature and the pH of the water and the amount of moisture that they get. So that's the ecosystem. If we look broader than that, the next one would be biome. Biome are going to be areas that have similar climate, so that's going to be similar water and temperature over a long period of time. We've got a number of biomes on our planet, so I'm right here in the northwestern coniferous, not quite in Canada, but right there. But we're going to have deserts, we're going to have rainforests, we're going to have the taiga up here, we're going to have the polar areas. So these are all biomes, larger areas where they have similar climate. And then finally we have the biosphere, and that's wherever life is on our planet, which is pretty much anywhere there's water on our planet, you're going to find life there. And so Babekpo shows us the levels all the way from biosphere down to organism. But we're dealing with community in this podcast, talking about how populations interact and how populations change over time. And so if we lay it out, basically communities have structure. It's based on what species are found there and what's the total diversity of species in that area. Those species are going to interact, and one of the intimate interactions is something called symbiosis. Example I'll talk about is the leafcutter ant. Communities are made up of populations, and populations change over time. One of the ways they change over time is they grow. All populations will undergo exponential growth as they start to take off, but eventually they hit some limiting factors. Some of those are based on their density and some are not, and those are called density dependent and independent limiting factors. And so even though all life starts at exponential growth, it'll eventually reach logistic, or it'll bounce up and down for a long period of time. And then if we look at growth, population growth in humans, the study of that is called demographics. And so I'll end by talking about what we can learn by studying human population growth on our planet. So let's start with a community itself. Remember, a community is going to be made up of various populations. And so the first thing to look at, this is that picture I took here just about a month ago before the snow came. And this would be up at Highlight Reservoir. And so if you look here, we mostly have pine trees, you can see. But if I were to count all of the different pine trees that we have, so we've got a lodgepole pine and we've got an Engelmann spruce or whatever, if I were to go through and in a large area count all the different types that we have and how many there are of each and put those in a pie chart, that'd be species composition. Another thing in a community then is the total diversity. Not only, what's the largest amount that we have here, but what's the total amount that we have. And so this would be all the fungi they were able to collect in an area. And so that shows us species diversity or biodiversity in an area. And if I were to pose the following question, on our planet, so if this is our planet right here and the equator is here, where are we going to have the greatest species diversity on our planet? You might think, well, right here on the equator, it's going to be the most amount of light, but we'd actually find not. If we were to graph it, so if we were to go from the equator and we were to go to the poles and we were going to look at just diversity, we'd find that at the equator it's kind of stagnant. There's not a lot of movement of the weather, and so we're going to have low species diversity. It'll actually peak out where we have those rainforests, and then it'll eventually drop off, obviously, into the poles. So there's going to be less species diversity there. But that's community structure. What's there and how much total is there? Now, there's also going to be interactions between the populations there, and we call that symbiosis. Symbiosis, scientists say, it's living together. And so they kind of break it into 3 different ways that you can live with other organisms. You can live mutualistically, where you both help. You can live parasitically, where you're damaging one. Or you can live commensalism. And so basically that's somewhere in between, where you're not harming them. I kind of think you're either helping or harming if we look at these relationships. But let's go to a really cool one. This is symbiosis in leafcutter ants. Leafcutter ants, I'm sure you've seen the video. They cut a leaf off and then they'll carry it back underground into their mound. Basically what they do is they feed it to a fungus. So there's a fungus within that leafcutter ant colony. This is the queen ant. They're just giant compared to the other ants. But basically what they're doing is they're chewing up the leaf and they're feeding it to the fungus. The fungus then breaks down the cellulose inside there and produces this sugar that the ants can then eat. And so that's a symbiotic relationship now between the ant and the fungus. The fungus gets a constant supply of food, a place to live, and then it's going to provide food for those ants. And when they form a new colony, they'll carry the fungus with them. So they're really farming that fungus. Now, it even goes deeper than that. So when scientists were looking at this farming of the fungus, they found that the fungi are never infected. So there's never an infection in their farm like we have in our farms. And what they found is that when you look at the ant itself, there's actually bacteria living on the ants, especially high in the ants that are working in this farm. And so those are similar to some of the fungi and some of the bacteria that we use to make our penicillin, or to make our antibiotics, And so now we've got a mutualistic relationship between this bacteria that's living on the ant and the ant itself. And so it's evolving. It's also has this symbiosis with the fungus, and so it just keeps going and going and going and going. And so these are all symbioses, or these interactions between populations. Some are good, but obviously if I'm a tree living right next to this, maybe it's bad for me as a tree. Okay, so let's go to growth then. So within a community, we have populations, and populations are going to change over time. As they start to grow, all populations will undergo exponential growth. In other words, even though elephants might have a gestation of almost 2 years, if you have elephants in an area, that one elephant is quickly going to become 2 elephants, which is quickly going to become 4, and then you get this characteristic exponential growth pattern. So if you were to, this is just a mathematical model of exponential growth. This is actually human growth. And so here's humans from 10,000 BC until the year 2000, where the population hit 6 billion. We're going right at about 7 billion right now. And so if you look at this, this would be exponential growth. In other words, it's just taken off, especially since the Industrial Revolution. But you can imagine that it can't do that forever. So our population is eventually going to hit some limiting factors. We're going to run out of food, we're going to run out of space, disease is going to take over. And so we call these things limiting factors. And they come in 2 different types: density dependent. Density dependent are based on the size of the population. So an example would be, a lack of food would be a density dependent limiting factor. If there's no food, if there's no space, if we have disease take over because we're living in close proximity to each other, then those are all density dependent limiting factors. So that's going to limit the growth. Density independent are going to be those that aren't related to population size. So what are they related to? They're related to chance. And so a giant volcanic eruption, it's just chance, is still going to limit growth, but it would be density independent. Or a tsunami killing, thousands and thousands of people would be an example of a density independent limiting factor. And both of these are going to act on that exponential growth, and they're eventually going to level it off. And so eventually all populations will undergo what's called logistic growth. And it'll approach something that we call up here a carrying capacity. In other words, it's the area, it's the maximum number of individuals that an area can support. And so our planet has a carrying capacity. And so human population growth won't go on forever, because we're eventually going to run out of supplies, food, and space would be one example. And so logistic growth is that leveling off. And there are some populations that will quickly go exponential, and then they'll just die off, and then they'll go exponential again, so like a boom and bust cycle. But generally, if you're humans, if you're like humans, where it takes a long time to reproduce, and you don't have a lot of offspring, then you'll eventually approach what's called logistic growth. And so this is from the UN projection. So this is right here, we're in 2011. Our population is right around 7 billion on the planet. And so this is what the UN predicts, that this would be the high end. So this would be the maximum our population could get to by the year 2100, and this would be the low end. But the neat thing about this chart is they break it down by different continent. So here would be in Asia, here would be Africa, so this would be the high end, low end. So they've got a high end in Asia of saying by the year 2100, which I probably won't be around then, but they're saying that on the high end, you could have in Asia, you could have almost 8 billion people living there. And so what's the world population going to do? It's eventually going to approach what's called logistic growth. But it depends on where you are. So in the United States, if we didn't count immigration, we would actually be at logistic growth. We're actually leveling off in the US right now. And so that graph doesn't tell us everything. If you really want to know the answer, you have to look at what's called an age structure diagram. An age structure diagram, to kind of lay this out for you, what we have are guys on one side, girls on the other. So this is in Angola, and we'll compare that to the US in just a second. And so this is the number of individuals in this study who are from 0 to 5, and the number who are from 5 to 9. And so we sometimes call this an age structure. We sometimes call it a population pyramid, because you get this pyramid shape. And so if you ever have a pyramid shape like this, where we have, most of our population is really, really young, this is a population that's going to go exponential. So it's going to take off, because we have all of these young kids. They're going to produce young kids, and so it's going to be exponential growth. If you look at the United States, it's not going to look like that. So if you look at the United States, it looks quite a bit different. And so we have a lot of people that are older, but we also have this bubble right here in the middle. Those would be the baby boomers, if you know anything about the history in the United States. And then it's kind of dropped off here at the bottom. And so as it drops off at the bottom, that means, since it's pretty flat going across, this is a population that's going to go logistic, so it's approaching logistic. And sometimes you'll see age structure diagrams that are actually, they go in quite a bit at the bottom, and those are going to be ones that not only have they leveled off at some kind of a carrying capacity, but they're actually dropping off. Italy's an example of a country I know that's dropped off quite a bit. And then if we look at China, for example, where we saw a huge amount of growth, there's some interesting things here. This would be the typical population pyramid at the top, so they were undergoing exponential growth. But then they realized that, and they had this one-child policy, and so there was this decrease. And so they're going to level off, and India is actually going to take off and be the most populous country on our planet. And so are humans going to hit all these density-dependent limiting factors? Probably not, because we're able to figure out new ways to get resources, new ways to get energy. But eventually, I'm not pessimistic. I think humans are eventually going to kind of reach a logistic kind of a pattern, and we're going to kind of stabilize. I don't know, 10 billion, something like that. That's my guess. But again, I'm not going to be around, so it's no big deal. So that's community interactions, and I hope that's helpful.